In October 2018, inside a civil engineering lab at the University of Cape Town, South Africa, a master's student named Suzanne Lambert held up something that looked impossible. A solid rectangular brick. It rang when you tapped it. It held weight. And it was made from sand, bacteria, and human urine. No kiln, no furnace, no cement. The brick formed at room temperature in a mold through a biological process that scientists compare to the way seashells grow on the ocean floor. That single brick cracked open a question that runs deeper than most people realize. If biology can turn loose sand into solid stone, why has no one told you about it? Why is there no product on the shelf? And what else can your own body manufacture that the modern supply chain has trained you to buy? Welcome to Oracle Prime. Today we are pulling apart the science of biocementation, the ancient observations that first noticed it, the modern laboratories that proved it, and the real reasons it has not reached your hardware store. By the end, you will know exactly how this process works, what it can and cannot do, and how to test it yourself. Stay until the end because the DIY section is more detailed than anything else you will find on this topic. The true price of modern cement. Before we talk about what could replace cement, we need to understand what cement actually demands from the planet. Because the cost is not just financial, it is geological. To make Portland cement the foundation of virtually every modern building, road, and bridge, manufacturers must mine limestone, crush it, and heat it in rotary kilns to temperatures above 1,400 degrees Celsius. That extreme heat triggers a chemical transformation called calcination, which releases massive quantities of carbon dioxide. The cement industry alone accounts for roughly 7 to 8% of all global CO2 emissions, according to the International Energy Agency. That is more than the entire aviation industry, more than every airplane on every route in every country combined. The infrastructure required to produce cement at scale is staggering. Mining equipment, rotary kilns the size of apartment buildings, grinding mills, and distribution networks that span continents. The barriers to entry are enormous, which means a small number of corporations dominate the global supply. The industry was valued at approximately $385 billion annually as of 2024. None of this is a secret. It is simply the reality of how civilization currently builds. And for a long time, there appeared to be no alternative. But the Earth had already solved this problem billions of years before humans arrived. How the Earth has been making stone for 2 billion years. Pick up a piece of natural sandstone. It feels permanent, heavy, ancient, and it is. But sandstone was not always stone. It started as loose sand, just like what you find on a beach. What turned it into rock was a microscopic process that has been running on this planet since long before the dinosaurs. The process is called microbially induced calcite precipitation, or MICP. The name sounds complicated, but the mechanism is elegant in its simplicity. Certain bacteria, naturally present in soil almost everywhere on Earth, produce an enzyme called urease. When urease encounters urea, a nitrogen-rich compound that mammals excrete in their urine, it breaks the urea molecule apart. That chemical reaction releases carbonate ions into the surrounding liquid. If calcium is present, and calcium is abundant in soil, seawater, and inexpensive powders like calcium chloride, those carbonate ions bond with the calcium and precipitate out of solution as calcium carbonate. Calcium carbonate is calcite the exact same mineral found in seashells, stalactites, coral reefs, and the limestone cliffs of Dover. It is one of the most common minerals on the planet. In nature, this cementation process happens over geological timescales. Sand grains on an ocean floor slowly get coated and bonded together over thousands or millions of years, eventually forming the sedimentary rock we call sandstone. But here is the critical insight that changed everything. Bacteria accelerate this process from millennia to days. When you introduce the right bacteria, the right urea source, and a calcium supply into a container of packed sand, the bacteria colonize the grain surfaces and begin precipitating calcite crystals that glue each grain to its neighbors. Within 72 hours, what was loose sand becomes solid stone. The Earth has known how to do this for over 2 billion years. Humans just recently figured out how to speed it up. Ancient observers, modern scientists. Long before any laboratory confirmed MICP, human beings in arid regions noticed something strange. Sand near livestock pens hardened into a crust that resisted erosion. Soil around tanning operations, where animal hides were soaked in urine, developed an unusual rock-like firmness. Desert communities observed that certain wet sand formations set into durable surfaces over time, while dry sand nearby remained loose. They had no name for the chemistry, but they recognized the pattern. Urine plus sand plus time equaled something harder than either ingredient alone. This observational knowledge threaded through practical traditions for centuries, rarely written down, existing in the realm of folk practice rather than formal engineering. Meanwhile, for most of recorded history, builders used binding materials that nature provided directly. Slaked lime, volcanic ash, crushed shells, and clay were the standard mortar ingredients across civilizations. Cathedral builders in medieval Europe added animal fat and hair to their lime mortar to improve flexibility. These materials held structures together for centuries, and many of those structures still stand today. The arrival of Portland cement in the 19th century did not replace these older methods because they failed. It replaced them because cement could be manufactured consistently, at scale, and sold as a standardized industrial product. Unpatentable, locally sourced binding methods do not generate shareholder returns. They do not create supply chain dependencies, and they do not fill a branded bag. That economic reality, not any conspiracy or active suppression, explains why ancient binding knowledge faded from mainstream awareness. There was simply no commercial incentive to keep it alive. The laboratory evidence, 3 breakthroughs on 3 continents. The science of biocementation is not fringe. It is not speculative. Hundreds of peer-reviewed studies across 5 continents have confirmed that MICP works. But 3 specific breakthroughs deserve your attention because together they tell a story of escalating ambition. Cape Town, 2018. The first biobrick from real human urine. Suzanne Lambert and fellow student Vukita Mukhari, working under Dr. Dylan Randall at the University of Cape Town, produced the world's first documented biobrick made directly from collected human urine. Previous experiments in the United States had used synthetic urea solutions, but the UCT team was the first to use the real thing, collected from specially designed urinals on campus. The bricks were grown at room temperature in molds, no kiln firing, no carbon emissions from production, and the process generated useful byproducts. The nitrogen and potassium recovered from the urine could be converted into commercial-grade fertilizer. Dr. Randall called urine the liquid gold of wastewater, noting that it accounts for less than 1% of domestic wastewater by volume, but contains 80% of its nitrogen. It is important to be honest about the limitations at this stage. The UCT biobricks were a proof of concept. They required approximately 25 to 30 liters of urine per brick. The strength was comparable to low-grade masonry units, suitable for non-load-bearing applications, but not yet competitive with high-strength construction bricks. The researchers themselves acknowledged that the major challenge ahead was scaling up urine collection and optimizing the process for cost-effective production. Stuttgart, 2023 to 2025, cracking the strength ceiling. Researchers at the University of Stuttgart tackled the biggest criticism of biocementation, that it was too weak for structural use. In their bioconcrete research program, the team achieved a compressive strength exceeding 50 megapascals using technical-grade urea, which is the purified form of the same compound found in urine. For context, structural concrete typically needs around 40 megapascals to meet load-bearing building codes. They had beaten the benchmark. But here is the honest caveat that most sources leave out. When the Stuttgart team switched from technical urea to real human urine, their results dropped significantly, approximately 20 megapascals with synthetic urine and around 5 megapascals with actual human urine. The bacteria lost activity over the 3-day biomineralization period when exposed to the complex chemistry of real urine. The researchers stated openly that achieving 30 to 40 megapascals with human urine, enough for 2 to 3-story buildings, is the target they are working toward, but have not yet reached. This matters. It means biocementation has proven its ceiling is high enough for structural applications, but the path from lab-grade inputs to a real-world biological waste stream still has engineering problems to solve. Edinburgh 2014. From lab bench to furniture. While scientists pursued structural benchmarks, a graduate student at Edinburgh College of Art named Peter Trimble asked a different question. Could biocementation make useful objects right now, without waiting for industrial scale? His thesis project, called Dupe, was a portable machine built from a repurposed coffee pump, a blender mixer, a mold, and a tank. He injected a urea and bacteria solution into sand-filled molds and produced a stool that supported 91 kilograms of weight. Trimble's contribution was not about breaking strength records. It was about demonstrating accessibility. His machine required no industrial equipment. The raw materials were cheap and widely available. He showed that biocementation could be performed at a small, practical, personal scale, and the result was a real, functional object you could sit on. Healing old stone with living chemistry. Beyond new construction, MICP has shown remarkable promise in one of the most delicate fields imaginable, restoring ancient heritage structures without damaging them. Researchers in Granada, Spain, applied bacterial calcium carbonate treatment to 16th century stone monuments, including the Hospital Real and San Jeronimo's Monastery. The results were striking. The treated stone gained measurable hardness improvements in the first 3 to 5 millimeters of depth. New calcite crystals grew epitaxially, meaning they aligned with the existing crystal structure of the original stone rather than forming a foreign coating. Color change was negligible, measuring below the threshold visible to the human eye. In Nanjing, China, researchers applied MICP to repair surface cracks in the bricks of the ancient city wall. The technique improved water resistance and compressive strength, and the newly formed calcite matched the morphology of the original brick material. Chinese researchers also tested the process on replica models of the Dazhou stone carvings, a UNESCO World Heritage Site, and found good adaptability in terms of strength, color match, and porosity. Field trials were conducted at the Potala Palace in Tibet, where biogrouting was tested on deteriorated masonry. Visual inspection showed that biomediated sandstone was the only repair material that survived the extreme temperature swings between day and night without developing visible cracks, outperforming both lime and conventional cement repairs. The key advantage of MICP for heritage work is what it does not do. It does not seal pores, it does not change color, and it does not introduce synthetic chemistry that could react badly with centuries-old materials. Biology grows compatible stone from within the existing structure. Why you cannot buy this at a hardware store. If biocementation has been proven in labs on 5 continents, demonstrated in heritage restoration, and shown capable of exceeding structural concrete benchmarks under controlled conditions, why is there no consumer product? The answer is not a conspiracy. It is economics and engineering. And understanding the real barriers is more useful than a villain narrative. First, the biology problem. The bacteria that drive MICP, primarily Sporosarcina pasteurii, need to be cultivated in controlled conditions. They lose viability when stored for long periods. They lose activity in the complex chemical environment of real human urine. Scaling bacterial production to industrial volumes while keeping costs competitive with a 50-pound bag of cement is a genuine unsolved challenge. Second, the consistency problem. Portland cement is an industrially standardized product. Every bag performs predictably. Biocementation depends on living organisms whose activity varies with temperature, pH, oxygen availability, sand grain size, and the specific chemistry of the urea source. Making biological manufacturing as reliable as chemical manufacturing is a hard engineering problem. Third, the incentive structure. Urea is unpatentable. The bacteria are naturally occurring. Calcium chloride is a commodity chemical. No company can build a high-margin proprietary product around freely available ingredients. This does not mean anyone is hiding the science. It means the usual commercialization pathway, where a company patents a process and invests in product development, does not apply cleanly to something that nature gives away for free. The result is a gap. The knowledge lives in academic journals. The researchers publish openly. But the translation from published science to a product you can buy requires investment that current market incentives do not strongly support. This is the same pattern we see with every unpatentable solution. It works,
it is proven, and it waits.
The Oracle Prime DIY Guide, Growing Your Own Stone. With all of that context in place, here's what you came for: the actual procedure. This is not theoretical. This is a protocol derived from published university research, adapted for a home experiment. Treat this as a proof of concept project, not a construction method. What you need: sand. Clean silica sand, the kind sold at hardware stores for landscaping or sandblasting. Coarser sand works better than fine sand because the larger gaps between grains allow the bacterial solution to flow through the entire mass. Avoid clay-heavy sand or very fine powders for your first attempt. Calcium chloride. Sold at hardware stores as a water hardener for pools or as road de-icer. A 10-pound bag costs roughly $8 to $12 and contains enough calcium for multiple test batches. Urea source. You have two options. The easiest is agricultural urea, sold as a fertilizer at garden supply stores for a few dollars per pound. It is chemically identical to the urea your body produces. If you want to test the full biological cycle, diluted human urine at a 1-to-1 ratio with water also works, as confirmed by the University of Cape Town research. Be aware that using urine produces a strong ammonia odor during the process. Work outdoors or in a well-ventilated area. Bacterial culture. Sporosarcina pasteurii is the most studied bacterium for MICP and can be purchased from biological supply companies. Alternatively, researchers have documented that native soil bacteria, particularly from garden soil or forest floor soil, contain urease-producing species that can drive the same reaction when stimulated with urea. You are not introducing an alien organism. You are feeding microbes that already live in the ground. A mold. Any rigid container works. A small wooden frame, a plastic box, a section of PVC pipe. The shape of your mold is the shape of your finished stone. The procedure. Step 1. Pack your sand firmly into your mold, but not so tightly that you eliminate all airspace between the grains. Think firm, not compressed. The pore space is where the bacteria will live and work. Step 2. Prepare your bacterial solution. If using a purchased culture, follow the supplier's instructions for concentration. If using soil bacteria, mix a handful of healthy garden soil into water, stir, and let the soil particles settle. The cloudy liquid contains your working culture. Pour this solution slowly over the packed sand and let it percolate through. Allow 4 to 6 hours of dwell time for the bacteria to attach to the grain surfaces. Step 3. Prepare your cementation solution. Dissolve approximately 100 grams of urea and 110 grams of calcium chloride in 1 liter of water. This is your mineral feed. Step 4. Pour the cementation solution slowly and evenly over the sand, letting gravity pull it through the entire column. The bacteria on the grain surfaces will immediately begin breaking down the urea, releasing carbonate ions that grab the calcium and precipitate as calcite crystals directly onto and between the sand grains. Step 5. Repeat the cementation solution flooding 2 to 3 times over the next 72 hours, with 6 to 12 hours between each application. Each round deposits another layer of calcite, deepening the bonds. Step 6. After the final application, let the material cure at room temperature for an additional 24 to 48 hours. Then unmold it. What comes out will look and feel like sandstone because chemically and structurally it is sandstone. The color will match your starting sand. Brown river sand produces brown stone. White beach sand produces cream-colored blocks. If you mix in iron-rich soil before packing, you will get warm terracotta tones. Honest limitations of DIY biocementation. Your homegrown stone will not be structural grade material. Expect compressive strength in the low single-digit megapascal range, roughly comparable to soft natural sandstone or rammed earth. This means it is suitable for garden pavers, decorative blocks, planters, small retaining walls, and artistic objects. It is not suitable for load-bearing walls or foundations. The process works best in warm conditions, roughly 20 to 37 degrees Celsius. Cold temperatures slow bacterial activity significantly. Urine-based solutions produce strong ammonia odors. Work outdoors. Cementation depth is limited. Lab-optimized setups have achieved cementation up to about 140 millimeters deep. Thicker sections require more sophisticated injection methods. None of these limitations diminish what this process demonstrates. You are watching biology build rock in real time. That is worth experiencing even at small scale. What this technology means for the future. The significance of biocementation extends far beyond backyard experiments. Think about the places where this technology could matter most. In sub-Saharan Africa, where the cost of imported construction materials excludes hundreds of millions of people from permanent housing, sand is the most abundant local resource. The bacteria are already in the soil. If the engineering challenges of scaling and consistency are solved, communities could build durable structures from materials beneath their feet. In coastal regions facing erosion, researchers have shown that MICP can be applied directly to shoreline sand, hardening it into beach rock that resists wave action. This is not a theoretical proposal. Field tests have demonstrated it. For disaster relief and remote construction, where hauling bags of cement over broken roads is slow, expensive, and sometimes impossible, the ability to manufacture a binding agent from local sand and biology could change the logistics of emergency shelter construction. The United States Department of Transportation has funded research on using MICP to stabilize sand around bridge pilings and levees, preventing the kind of soil erosion that leads to devastating infrastructure failures during floods. And every single one of these applications produces zero kiln emissions, zero coal, zero rotary furnaces heating limestone to 1,400 degrees. The carbon footprint difference between MICP and Portland cement production is not marginal. It is foundational. What you now know. Let me take you back to that lab in Cape Town. Suzanne Lambert, a graduate student with a mold full of sand and a supply of urine from campus urinals, grew a brick at room temperature that represented a genuine alternative to one of the most carbon-intensive materials in human civilization. She did not have a billion-dollar factory. She had biology. Since then, Stuttgart has proven that the same chemistry can exceed the strength of structural concrete. Edinburgh has proven that you can do it with a coffee pump and a blender. Granada and Nanjing have proven that it can heal centuries-old stone without leaving a trace. And the bacteria that make all of this possible are already living in the dirt beneath your feet. This is not a conspiracy that someone hid from you. It is a technology whose economics do not fit the standard commercial model. Unpatentable ingredients, freely available biology, no recurring revenue, no branded bags. The market did not suppress it. The market simply had no mechanism to sell it to you. But knowledge does not need a supply chain. You now understand how calcium carbonate bonds sand into stone. You know the bacterial species, the chemical ratios, and the procedure. You can test it in your backyard this weekend with a bag of sand, some pool supplies, and a container. Start with a small block. Run the process, wait 3 days, unmold it. Hold what comes out, a piece of stone that living organisms built at room temperature using chemistry your own body participates in every single day. Then multiply that in your mind. A garden path, a retaining wall, a planter, a floor. Built from the ground up by biology, without a kiln and without a bill. If this changed the way you think about building, share it. The knowledge only stays buried in academic journals if the people who find it stay quiet. Subscribe to Oracle Prime and stay close, because what comes next goes even deeper into the survival knowledge that economics forgot to commercialize. Until next time, stay curious and stay self-reliant.